So natural growth, the law of natural growth is the rule that governs when the rate at which a certain amount of stuff changes. So you could talk about the population changing or the amount of radioactive material changing, and the rate at which that changes is related to how much of the amount that is present. So in mathematical terms, what we're saying is that let's say we've got something that we're measuring y. It could be a population, could be the temperature of something, it could be the radioactive material of something, and it's changing over time. So that's dy by dt. It's a rate. And we say that that's proportional, there's the symbol for proportional, to the actual amount of material that's present. So that's called the law of natural growth. You guys have probably already encountered it, and they're called growth and decay problems. And I am going to show you how to derive a solution to this. This is a proportional equation. So I'm going to change that to the equal sign and introduce a constant. So it's proportional means as one goes up, the other goes up. And now I have an equation. This is called a differential equation. Why is it called a differential equation? Because it has a derivative in it. And I'm going to solve that. And there's two variables and a constant. So here's my constant, and my two variables are y and t. So I'm going to separate these variables to be on separate sides of the equation. So right now it looks like I've got dy, t's and y's on the left side, and I'm going to separate it by interpreting these as differentials. So I'm going to move the dt over to the other side by multiplying both sides by dt. And I'm going to divide both sides by y to move the y over to the left side. So notice I have separated the variables. And in further math courses, you're going to be dealing with way more complicated equations than this one. This is called a first order differential equation, and it's quite simple. And we're solving it by separating the variables. So this is a method that you're going to encounter more often as you move on in different math courses. Now if I want to find out what y is in this case, I have to get rid of these dy's, and one way to do that would be to integrate. So what I do to one side, I have to do to the other. So I'm going to integrate, and let me just scroll down here. So if I integrate, this is integrating 1 over y dy and integrating a constant with respect to time. So the integral of 1 over y would be the natural log of y, and we have to make it an absolute value, but for most the decay problems it will always be positive. And k, it will be kt, and we have to introduce a integration constant. Now I want to get y all by itself, so I am going to write this as an exponent. So the y equals e to the kt plus c. So all I'm using there is, if I had, this would be written as e to the b equals a. Same principle. So this time my variables are a little bit more complicated. Now I'm going to do one more trick, which is to separate out the c. So if you can imagine that you were multiplying these two, you'd have to add the exponents, which would give you back to this. So I'm going to write it this way and then say what happens when t equals 0. Well, when t equals 0, I have y equals e to the c, and this is e to the 0, so y equals e to the c when time is 0. And when time is 0, we have our initial amount. So we call the amount we have is y0, which is stands for the initial amount of the substance. So that means that this can be written as the initial amount. And putting it all together now, we've got a, give me some more room here. If we start off with an equation where I use P now, I should use Y. If we start off with an equation where we know the Y function varies with time proportional to the amount present, then we know the solution to this, based on the proof that I've just done, is that, where Y0 is the initial amount, and K is a constant, and it represents the rate constant. It's called the rate constant. So we are going to apply this rule to many types of problems, including population problems, radioactivity